Hi, I'm Stephen Rowe, and this is my deep learning project, building a unit for Mars rover hazard detection and avoidance. So the motivation behind this, if you think of the Mars rovers, currently Perseverance is on Mars. It was launched and landed on Mars back in 2020. There are kind of two main things that go into driving a rover autonomously on a different planet. Number one is there's large-scale path planning, basically where a NASA engineer looks at a satellite top-down view and clicks a point, gets GPS coordinates, and sends it to the rover. And then while it's traveling from point A to point B, it also has to be able to do small-scale hazard avoidance. So if you look at this picture on the right, is just kind of a big boulder field, and so it has to be able to avoid all of that because it's this multi-billion-dollar robot that you don't want destroyed while it's driving along. And so you just have to be able to detect those things with the onboard cameras. Currently, the Perseverance rover does have a deep learning model that it runs for hazard detection. But with all the recent advances, both in computing power and in deep learning in general, I believe that the potential for something like this is a lot greater for future rovers and for future missions to Mars. And so the goal for this project was to create a unit that you could use to process images for obstacle avoidance. I also wanted to be able to calculate a driving vector to determine where the rover should go based on its immediate surroundings. And in order to do this, NASA has published a data set from images from Perseverance and Curiosity and Opportunity called the AI for Mars data set, published by NASA JPL. And it has thousands of images from Perseverance and other rovers. But it also comes with not just the images, but also like label masks. So each pixel has been labeled by about 10 people, and they categorize them as either soil, bedrock, sand, or big rocks. And then there's a fifth class that's just unlabeled. That would be for something like the sky, or if the picture has part of the actual rover itself in it. And I just decided to ignore those because I just wanted to train on the Martian terrain rather than other objects. So the first thing I had to do after downloading the data set, which was huge, it was like 16 gigs, took forever. But I had to decide which images I wanted to use for training. And so the following criteria are what I used to determine which images I wanted to use. Number one is it had to be mostly Martian terrain, right? If it was mostly rover or mostly sky, then it wasn't really that useful for training. So I got rid of everything that was not terrain. I also wanted to make sure that there was a corresponding label mask with each image. And then there were also a couple of different labeling schemes. So I mentioned that each image was annotated by about 10 people. Sometimes those people were geologists who cared very much about, is this sand? Are these pebbles? Are these big rocks? Are these rocks angled? Are they flat? Like they cared mostly about the geography of Mars rather than trying to drive the rover. And so the geo labels were kind of clunky. There were a lot of them. There were 22 labels, and it wasn't super clear which ones were safe terrain versus unsafe terrain. But then the other set of people who were labelers was the navigators. And so they only had the four labels that I already mentioned. And so I decided that those were going to be my criteria, and I ended up getting 823 viable image mask pairs. And those pairs are shown below. As for the architecture of my model, I mentioned before I'm using a UNet because those are particularly good with image segmentation, and they're also good at doing pixel by pixel analysis. And so the inputs to my model were just the images, a 3-channel RGB input, and then the outputs were basically like the probability of each pixel being a certain class. And I'll get to more about how I process that later. So yeah, the images were resized down to 256 by 256 pixels, and then they were passed into the model, and then the classes were determined from there. As for the architecture code-wise, here's what it looks like. I won't go into too much detail, but you can see some of the parameters, kernel size 2, stride 2. There's also the double conv class that it calls here. and that is shown here. So this is the actual architecture, and you can see it's two convolutional 2D layers along with some batch norm and ReLU activation functions. And then model parameters. This is just kind of a summary of the last couple slides, I guess, but the loss function that I used was cross-entropy loss because that's good for image classification. I also used the ignore index 255 flag just because, as I mentioned before, not every pixel is terrain. Some of it is stuff that wasn't useful for training. I trained for 60 epochs. My first training run was actually 15, and that didn't do too well, so I upped it to 60, and that seemed to work. And then, yeah, the rest of that is pretty standard. So yeah, the general pipeline, get the images, resize it to the UNet 256 by 256. Also to increase robustness in my earlier training runs, they didn't do very well, and I'll show a picture of that later. But it tended to learn the color of the pixel rather than the texture itself. And so I used some random grayscaling to help it learn the textures a little better. And so then once I'd done that, I passed it into the UNet, got a probability map, and then I used a nearest neighbor interpolation. So rather than blending classes, right, like rather than saying this pixel is somewhere between a 2 and a 3 for the labels, I just wanted to say pick one of the classes, right? So rather than being somewhere between sand and rock, it's only one or the other. And so that gave me these results. The first test, again, this was the 15 epochs instead of 60. This was also without grayscaling initially. So this first image, it just thought everything was sand because it had only seen kind of white pixels as sand before. So after retraining, you can see the mask down in the bottom image was much better. And so for these images, gray is bedrock, brown is soil, and those are categorized as like safe places for the rover to drive. And then orange is sand, and it's not shown in this picture, but red is big rocks. And so sand and rocks should be avoided. So after getting the retraining, I did actually use some of the geo labels that I mentioned earlier. I tried to like map the geo labels to the nav labels. That didn't work too well. You can see it generally got the terrain correct, but then the driving vector itself was just kind of off, and that's because it was just confused. Like, I know this is a rock, but I don't know if it's safe or unsafe, and so it just kind of drives wherever it wants. So after I fixed those issues by upping epochs, adding grayscaling, and changing the labels, these are the results that I got. And so I used a mean intersection over union evaluation. This basically says if you take the segmentation that my model created and the actual label mask from the data set, how close do they match up? And so for soil and bedrock and sand, it's pretty good. Generally for MIOU analysis, between 70 and 90% is a desirable range. Above 50% is okay, but 70 to 90 is kind of what we're shooting for. So generally, it does pretty well. And here are some of my images. And so here's the image that I passed in on top. And you can see it kind of determines where the sand and the soil are and creates a driving vector to kind of get around that sandy bit in the middle. This one kind of starts in the middle of a rocky field and tries to get out of it. This one just kind of stays along a bedrock section between some sand. This just avoids a boulder section off to the right. This one actually did pretty well determining sand versus rocks. And most of the image was safe, and so it just said, keep going straight, you're doing good. This one I thought was interesting. It's kind of already in the middle of the sandy area, but it just tries to take the most direct path to safe bedrock. And then I added this edge case where if more than 90% of the pixels in the bottom half of the image, right, so the most immediate area for the rover, then rather than publishing a direction vector, it just tells the rover to stop so it doesn't get itself into bigger trouble. So yeah, the conclusions are that I successfully made a UNet to predict pixels with about 80% accuracy, and I was also able to generate these commands to drive a rover. So next steps would be to add some new images for more training robustness, maybe add in those geo labels if I can figure out how to map them, and then add more classes and weights to kind of up that big rock MIOU value up from 56%. And then eventually the goal would be to actually implement this on a real Mars rover. Thanks for watching.